Yes, yes.
Of the meetups you guys have it. Um, Basically, it's a tool that we use for our visualization. So basically, I mean, a large part of what we do is generate a ton of charts. And we have to do this really quickly, and we don't necessarily deal with big data sets on a per chart basis, but we do have them. I mean, they're decent size, and we just need to be able to crunch a bunch of data about them. And it's kind of an ad hoc thing per chart. So Framien's really just trying to do that. And so it's basically, yeah, it's works with tabular data, so you kind of think of like a CSV file. It's kind of like, well, if we wanted to work with that in Scala, what would it look like? And the key kind of thing is it has to work with heterogeneous data, so it's not just like a matrix or like a bunch of numbers. It's got dates and text in there and, you know, categories and that kind of stuff. Obviously, it has to be fast, because I like things that are fast. And should be, you know, like, be able to handle real-world data. So, like, you know, we're quite often we're missing values, or, you know, there's errors in our values, and want to be able to make sure that those are handled in a sane way and not just, you know, thrown out. Yeah, so my disclaimer is basically that Fragment itself is still in beta. There's still a lot of changes as we kind of use it and we see what we need from it. So there's obviously a lot of bugs as well. Of course, it's in Scala. And the other thing too is like this. There's a couple branches that I use in this that aren't currently merged into master. One of them is CSV, which just redoes our CSV support. It's a lot nicer now, but just not in master yet. Same thing with a little bit of stats. So before anything, we're going to kind of have like a running REPL session in a way. So we have to basically import all this stuff, basically our framing things, but also you'll see that we have Spire there. Framion makes heavy use of Spire, partly because I am one of the co-authors of Spire, partly because it's also great. Okay, so frame, what does a frame look like? So here we're basically using the CSV object we have. We can basically parse it and turn it into a frame. So this is actually, you printed the toString for a frame, so when you run this, you'll actually get something that looks like this. All throughout these slides, I'm basically always cutting off a bunch of rows and a bunch of columns because this is a big data set. But this is kind of the data set we'll be working with through the entire presentation. It's kind of a well-known one. It just has a bunch of auto-carved data, so you have, like, you know, the main thing is you get the miles per gallon, you have all this data that is associated with the cars, and you can kind of try to figure out like what the miles per gallon are going to be based on the other parameters. There's a few things you'll notice. Our frame is generic. It has two types there. It's parameter has an int and a string. Those are actually the key values. So we have our columns and our rows. So our rows are keyed first. Those are ints. It's a CSV. So we have, like, you know, your first row is 0, obviously. You know, up from there, and then because we did two labeled frame, we also take the first row of the CSV and we say that that's actually how we want to index our columns. Yeah, so you can see our column rows here. Basically, it's a string. That's what it is. And then we have all our lovely data. And you'll notice here that while most of it's numeric, we also have some text data here. So that's kind of what I was driving back, is that it's a heterogeneous frame of data, not just a bunch of numbers. If you are kind of either been around Scala for a while or you've kind of looked at this stuff before, you'll know that this kind of looks like a library called Saddle. I must say Saddle is fantastic. It honestly is super awesome. Just that we were actually using it first. It just wasn't quite what we needed because the main thing is that Saddle's typed. All the values always have the same type. So they're numbers or dates or whatever else, but they always have the type of numbers. And so they do have some basic support for heterogeneous data, but basically what it is, they're saying it's anything, and then they just, you know, cast things as needed. It wasn't very nice, and it made that using it as a heterogeneous frame wasn't super great. So it made it difficult for our use case. So we built this tool to kind of deal with that. So as I said, ours does not have the value type. So it's kind of, I guess with Scala, you kind of expect to have types all the time, and we kind of throw those away. But you'll see that it doesn't really hinder us too much in this case. So the main thing is that whenever you access data, you have to specify the type. That's how things are typed. You say, get me the column as numbers, or get me the column as text. We have, this allows us a lot of flexibility too, because if you have a column and maybe it's full of integer data and you ask for it as a double, it should still work. I mean, you shouldn't have to know that whether the person gave you a column of doubles or big decimals or whatever. Yeah, so getting values out. So we loaded our frame earlier. So basically, one of the easiest ways is just to get a single cell of data out. So in this case, we had our two ways of indexing the data with the rows and the columns. So we're just saying, give us the 333rd row, 334th, I guess, really, your index, and column horsepower. And we get back value eventually. Yeah, so you get back to value, it has 132 horsepower. You see it has this little cell thing, we'll get to that in a second. Because you have that, say, well, give me the name of the same thing as a string. We get that, that's in 280ZX. Lovely. So you can see you can ask for the horsepower as a string. We do get back a value. And that's just because we generally say that we can turn things into strings. Because Scala. As I mentioned before, though, we are flexible. So, well, the horsepower is really like 132. If you ask for it as a big decimal, you should still get it back as a big decimal. If you want to deal with it, have more accuracy, you should be allowed to do that. Yeah, same thing, because it actually was an integer, it's 132. If you do ask for it as an int, it will return a value as well. And the main thing here is that we're working with numeric data in a frame. We're not working with like doubles or big decimals. We're just working with numbers, real numbers. So then there's the question of, what happens when things aren't so hunky-dory, right? So before, we're able to get the horsepower value out of that pretty easily. You can see in our table, it's right there. That's the row 333. There's a value there for horsepower of 132. But if you look a few rows down, for the Mustang Cobra, the horsepower column, which is right here, is actually missing. So when we ask for it, we actually don't get back the value. We get back sentinel value, NA. Basically says that this data value is not available. It's missing. Another thing is what happens if we ask for, say, the name as a double? It doesn't make sense. You can't turn that into a double. It's not a double. In this case, you'll get back another type of sentinel value called NM, which is not meaningful. So that basically means that there's some data there, but it doesn't make sense for how you ask for it or whatever.
Question.
Oh, yep.
So the difference between interpreting that dash as not available versus a string that did properly, is that a nuance of the extracting it from the CSV?
Yes, that's part of the CSV parser. So the CSV parser will try to auto-detect a lot of stuff. So they'll try to figure out what your missing values are, like whether it's like you've had n/a or dashes or just nothing there. They'll also try to figure out if column types are like numbers or text.
So and you can write your own extractor with CSV file and figure out if something else.
Yeah, I mean more than likely you'd use a different CSV format for the parser. Okay, so basically, the main thing I was driving here is we have these things called cells. Cells are kind of like the fundamental thing. They're a little zero-dimensional data structure that has a single value in it. So we have three cases, which is a value, yep.
So this is just maybe restating what you just clarified, but nonsensical means you can't parse it correctly with the target desired. Right?
Sorry, say it again?
When the NN.
Yes.
It means you couldn't parse this. There's something there.
Yeah, I mean, I'd say NM has a wider role of just, I'd say like NA is kind of like it's not there. NM is kind of like we had an error trying to get you a value.
So it could be, it could be a parse error.
Yeah, it could be like division by 0 too, right? Or something weird like that, I mean.
Sure.
Depending on what you want to classify. But the main thing is like a lot of values, like when we're doing reductions on the frame and stuff, we'll interpret NAs and M's differently. So we'll see that later, but yeah. Anyways, so basically, yeah. So our cell types have three values: the value, the NA, and the MM. So the value wraps a single value. It's basically saying there's something there, and here's the value. The NA is like, this is missing. The NM is this is nonsensical. There's a value here, but it's bad. So you can see it is very similar to option, except we've added one extra case. So option has it's here or not here. We have it's here, not here, or it's here, but it doesn't make sense. So obviously, getting at single values is kind of not super useful for a lot of people. We generally want to get out entire rows or columns or groups of columns. And so we do that with basically something called calls. There's also rows. We'll get into that later, but the main thing here is we basically have a couple parts, but the first part is we're basically giving it the columns we're working with. So in this case, the type that you're giving it, like this horsepower, has to match up with the column type of our frame. So our frame's column keys were strings, right? They're the headers for the CSV file. And so one of those is HP, so we use HP here. And then we're basically saying that we want to extract the horsepower column as a double. So that's what that does, and we'll get into how it works. But basically, you'll see here we get something called a series, which is basically a list of numbers that have keys and values. It's not a map because the keys can be duplicates; they don't have to be unique, and there is a natural order to them that may not be the sorted order. In this case, obviously it is, but you can see here that series as well have a natural notion of values or basically cells. All the values are cells, so they can be missing data in there as well. You can see here we have basically the key parameter for the series is the same as our rows. That's because we access the column, so we're getting all the rows, the that column from each of the row. And then the value is just our value type. So we have the corresponding rows, which basically, where columns is selecting a column, rows is selecting a row. And now we're saying get us all the values in the row as a string. And you see it'll rip it out, and we'll get basically a single row, which is kind of like a record of strings. Right, so this was basically a simple case where a single column, we're getting that out. Quite often, that's not all we want to do. You usually want to work with more than one column at a time. So you could, for instance, actually give it more than one parameter. So you can say I have only name and horsepower, and I want to give it as a two-tuple of string and double. So basically we're saying the name column is going to be a string, and the horsepower column is going to be a double. And then we finally run that, we'll get back a series, and you can see here it pulls out what we think it will. We have our rows, our keys, and then our values are two tuples of like the name of the car and the horsepower. If either of those values is NA, the entire thing will be an NA. So how this works is it basically just has a generic type class called an extractor. And the extractor basically knows how to get values out of the frame, or out of a bunch of columns, basically. So by default, we really just have the one, which is, I guess two, but one that uses H-lists and then has support for shapeless as generic. But yeah, the main thing is that both these things have a size associated with them that we know at compile time. And so we use the number of columns that you provide, like if you provide a horsepower name, you have two columns you're working with. So we know we have two columns we're working with, and we use that size at compile time to guide the inference. So that's why when we're extracting one column, we can say it's double and it works. And extracting two, we know that we have to work with something that's more complex, so like a two-tuple or each list of two size two. So here's a little example where we have a car case class with the three fields. We basically define our calls outside of here. Calls doesn't actually get any data by itself. It just creates sort of a description of how you get the data out of the frame. And you can just see here, we say as car. This is thanks to shapeless. Basically, shapeless has this thing called generic. It lets us basically, given a car, we know how to turn that car into an H-list and how to turn an H-list back into a car. So we can figure out how to actually extract those values. We can know it's a string double, and when we get the values out, we actually get out the series, and it's actually full of cars, which is pretty nice. To see here too, I did define this outside. I found in practice that it's very useful to generally define your call like how you're selecting your columns outside of the frame, not on like a per use basis, because that way you've kind of defined your way of extracting the values out as a type in one place, and everybody can reuse that. The main thing is these rows and calls. It abstracts how we actually get values out of a frame. Pretty much all of the useful operations on frame will take a column, other calls or rows, and work with those to actually get values out. Because obviously, in Scala, we need to actually have a type to pretty much do anything useful. It also lets us work with frame uniformly. So we had one get method that worked for both calls and rows. No matter whatever one you provide, it'll work. So you don't have to worry about getting the method names right. There's just one way, and you sort of define how you want to actually access the data, whether it's like along the row axis or the column axis. And so calls / rows are more than just saying like have more than just an add method on them. You can also you can map them, for instance. So we're in here, we have our calls. We're saying an origin field in our CSV. You want to get that as an int because it's just number 1, 2, or 3, and these correspond to some region where they're made. So in this case, we're basically just turning them into strings. We're saying, oh, if it's a 1, it's USA. If it's 2, it's Europe. If it's 3, it's Japan. So we have our, yeah, I don't know how to say it. But yeah, so you can see the result type of this call is now a string. So we're basically saying when you extract this, we actually want to get it as a string. It'll do the mapping as it pulls the values out. Here. Okay, so anyways, just other operations too, there's more than this, but basically you can zip them. So instead of like saying name NHP as a 2-tuple, you can just get from both single values and just put them together and get back to still. You can also recover from NAs and M's. So if you load a CSV, you want to basically fill in all your values with like the mode or mean or whatever else you want to do. There is a lovely recover function, so you can basically say, well, if it's NA, then just replace, in this case, we're saying if the horsepower is ever NA, just replace it with 100. And then when we go to actually get, like, say, this was the value I was missing before for the Mustang Cobra, when we try to get it now, it'll actually just give us it'll recover with the default value of 100 instead. Okay, so now we're going to move on to frames. And sort of what can you do with frames, some operations. This is just going to be kind of a wang bang, sort of just showing a bunch of different things you can do and kind of give you a feel for some of the stuff. So the first one's obviously just sorting. You quite often want to just sort things, so when you get them back out as a series, you have the order. So you just sort by just takes calls. So in this case, the horsepower is double and sort by that. You can see here, just put all the NAs first. So we have like 6 cars that don't have any horsepower value. And then we go on from there. So grouping exists as well. Grouping is not grouping in the SQL sense. Basically, the main thing here you'll notice is that the row index has changed. So before it was an int, it was the row. Now it's changed into a string. What's really happened is that we've made our row keys into our origin, and then we've then sorted the frame based on the keys. This has a couple of things. I mean, if there's NAs, they'll be dropped, which is important to know. The other thing, of course, is that grouping is, because obviously grouping what it really is equivalent to is like we basically just sorted it, and then there's another method called reindex, which basically swaps the index. It doesn't necessarily actually sort the frame. We can also map the frame. It's something you'll do quite a bit too. So basically, we say, okay, we want to extract some value as this, and whatever. We have 2 columns. This is the column we're going to store the result of this map into. So the actual function I'm doing here is I'm converting cubic inches to liters. That's because I'm Canadian and I understand liters. So basically, this is just a conversion factor. So we just have a function that takes cubic inches of the double, and we can just turn it into liters, and it'll get stored back in the frame. You can see here that there's a frame, and we've gotten our liters out, and they're sensible again. You can understand what's going on. A bunch of American cars, so obviously they're massive engines with pitiful amount of horsepower on that side. So now we have moved on to join. So obviously, like the whole point of this is really to take 2 things, like 2 CSVs, and join them together, or 2 whatever you want to do and join them together. We're going to do kind of a toy example because it's easy. So in this case, basically what we have is we have a frame that has very simple data. It has a single column. The rows are basically our country or our region of origin. So if you just say Europe and Japan, we're basically mapping them to a more readable human version of the same thing. The series just has a two-frame method. All it takes is the column key the single column is going to create for the frame. We get back frame. Yeah, it's lovely. So now we're going to take our frame that we had grouped by the origin. So the key is now the Europe, right? I don't remember if we slide back. We're going to basically drop all the columns but the name of the card because it'll fit on a slide. And then basically we're going to take that frame, we're going to join it with the frame we had defined previously here, and basically do an inner join, just outer joins, left outer joins, whatever you want. And then end up getting a frame with two columns, names, and then a human readable region of origin. Here, lovely. So yeah, this column came from by origin, and this column came from the original labels frame, and it's that's kind of the main reason why one of the indexes are not unique. Whenever we're doing joins or anything, we're doing it based on the row keys, and if all our row keys were unique, joins would be pretty boring. Okay, so then reductions as well. So I've just defined a bunch of calls up here. Like I said, it's kind of easier if you just define my calls up front, and then you don't have to worry about the types all the time. It's a little shorter. So basically, you can see we're calling f.get. So we're getting the horsepower as a series, and we're calling this value mean on the series, which is basically telling us that there was an average of 104 horsepower. I mean, keep in mind this data is like 30 years old or something. So back then, I guess that made sense, but not a ton of horsepower. There's other reductions you can call max. Quite a lot of good miles per gallon. I think most people here probably don't even get that. There's the ones like unique, so you can get all the unique values out, etc. You'll notice that every single one is always returning a cell. This kind of goes back to what I was saying before, which is like, so the reason why we have an A and M is that for an NA, we're doing a reduction, I'll just skip over it. It's just like, okay, well, it's not there, that's fine. You can deal with this in data. NMs are more saying that there's a value there, but we don't understand it, so we can't do the reduction. Like, how do you sum up X plus some value you don't understand? You don't. So we just bail out whenever we see an NM, basically. We can actually get a little fancier, too. The real reason why we have the keys are not unique is that we can do reductions by them, so this is more like grouping as you're thinking. So in this case, we have a series again. This time we're getting the average horsepower by the region of origin. I really want to say country, but I have Europe in there. You'll see that, yeah, basically, obviously, American cars have a lot more horsepower on average, but you also see that they have significantly worse miles per gallon on average as well. And so all of these things, when you put them together, you can start doing fancier stuff. This is kind of terrible. I will show you how we can do this in a fun line later on, but kind of go through it. Basically, what we have here is we're first getting the mean by origin, so we're just getting a series with three values, which is like what we had before. Same with the count, so we're getting the number of cars in each from each country of origin or region of origin. And so retain columns once again just for size because it's slides. Basically, yeah, we're going to take our average miles per gallon, we're going to join them back into the table. Our table has, all of the cars in it. Our mean miles per gallon by origin only has like three values in it. So basically, for each region of origin, I'll get the mean for that region of origin and apply that to every single car in there as a part of the column. We then extract out both miles per gallon and the mean as a two-tuple. So basically, at this point, we have a series of strings to two tuples of doubles. We then map these, and we basically are just saying that, okay, we're going to take the miles per gallon, subtract the mean from it, and then square it. Probably see where this is going. We then take the sum of all of them by piece, or back down to a series with just three values in it. And then we're basically going to divide. The zip map is basically like a join for series. It does an inner join and basically lets you give it a function instead because it has types. So in this case, you could take the count. So we have the sum of the differences of the sum of squares are the difference of the values by the mean, and then we are divided by the count, and so we have the variance, and then we're going to map this to the square root, so we have the standard deviation. So then I have the standard deviation in the miles per gallon for country of origin. You'll see that they're actually all pretty much the same, which means that the means we got earlier were pretty good representations of the actual horsepower of the car. They all have kind of similar shape of sorts. So yeah, there's that. So I just want to very quickly go over what framing is not, just so I don't get flack. But there's not about big data or distributed computing or anything like that. It really is all in memory. We're working with, not small amounts of data, but small amounts of data. So obviously, if you want to do bigger stuff, there's great tools out there already. It's also not a linear algebra library. We don't have any intention of being that. If you really want to, get a matrix out, then one of the libraries that exists out there, right, that are good at that. What it does try to do is it just tries to provide kind of a bunch of basic building blocks so you can build tools on top of it. So we have our way of extracting values from a frame, which are columns and rows. There's this kind of fundamental concept of an index, which is reused in both series and frames, and it handles things like reductions. So it knows about the keys and everything. They can do the grouping and sorting as well. I can also do co-grouping, which is how zip map and series and join and frame are implemented, and an operation called merge, which is weird. So it's kind of a nice thing to do. And then our column types are basically where we actually stuff the data. There's kind of two types of columns. One type of column is the type column. That's main goal is really to be very fast and let you just rip through values as close to as quickly as you could with an array. So we can kind of do these things fast. And the other type of column is one that kind of lets you figure out how to get a typed frame out from a bunch of possibly other types of columns. They actually let you do the casting. So yeah, like I said, our hope is that this will be used to build more complex libs on top. We kind of started the framing stats to do some basic stuff. I'm going to show you that we have the one-liner, so you can actually just use standard deviation here and get up the standard deviation. So in this case, power is our frame, so we're just saying we'll give the standard deviation for the column miles per gallon. Then here we're using there's a method to do ordinary least-squares regression on this. So miles per gallon is a dependent variable, and we can give it any number of independent ones. And then basically, once we have that, we have a classifier. We can basically then, I guess, rest really. And basically, we can try to predict what the miles per gallon will be based on the weight in the cubic inches. So you can see we have a 5-liter engine, and we're saying, well, what's the effect of the weight? You can see that, as you go lighter, your miles per gallon increases a lot. Yeah, so that's basically it. We're trying to get people to contribute and use this. So if you want to start contributing, you can start looking at some of the issues we have and tackling the problems. Yes. Yeah.
So it sounds like you're saying it's a column data.
It can be either. I'd say it's one of those. So there is two versions. There's a row-oriented frame and there's a call-oriented frame. So I would say you should know more or less how your data is stored. It's if you're doing CSV, I will say we do column-oriented by default.
For loading, row-oriented is better.
Yeah.
Slicing nice.
Yeah, yeah, and I would say framing, at least for our use case, a lot of it really is burning through columns. We have a column data where just, so
yeah, as long as you're doing more than just the cost of just loading things, switching the column.
Yeah. And yeah. It's definitely a.
There was a slide where you had it's break.get something, a map to meters, right? And
yes.
That function. Is that adding that column
yes.
to the frame?
Yes, it is. Yeah, it'll add the column to the frame. And actually, the behavior we have right now is that if the column exists, it'll drop that column first and then add it. And that was kind of I wasn't sure what the right behavior would be there, but I talked to a few people and they seem like common use case would be that they're replacing a column with something that they've done. So
it doesn't return a new frame.
No, it always returns a new frame. These are all immutable things. We're not copying all the data in the frame, but yeah, it's definitely returning a new frame. So your old frame will still not have that. The new frame will. Anybody else? Sweet.
Thank you.
the next one in like 5-ish minutes. Oh, you need to use yours.
Oh, yes. Oh gosh.
It's okay. I understand. You want to leave?
I was like, yeah, I'm just gonna leave you high and dry.
I need you to stop it because I have no idea.
Hey, how's it going? It's actually me. Yeah, I know, it's good. All these I see on Twitter and never in person.
Sorry, can you just go back to the Hangout again?
That is
You're left.
hopefully you can do that.
Cool.
And then you're doing.
I think, and then you
No, I will. There is so much stuff I need to do that is not existing right now.
I think you're going to want to see like it's my stuff. I'm not sure if it's for Linux.
Yeah.
I actually have some pretty good code.
So what we want.
So you want to send that one outside?
So you.
Presentation machine or?
Yes. Well, it's my machine, but he's gonna present from it because he uses Linux and it never works with anything with a projector.
I was just lazy to take
Sure.
it.
Yeah. No, yeah.
Kidding.
Who's live watching stuff?
This guy over
there
there.
actually is watching.
It'll be recorded at least.
Yeah.
Okay, I think you're actually good to go.
Can you
send
mute yourself?
Oh, right. I'm making sure it's on the live recording that nobody's watching, but not on the actual screen that has stuff. Oh, God.
I want to just screen size.
Yep. Well, it's on a VGA cable. I don't know. It's not. It's okay. Whatever.
Well, can say
Actually.
How do you full screen that stuff?
I forgot to unmute it.
All right. Thanks everybody for coming. This is the second talk from Two Talk October. This is Alexander Bartay. He used to be one of the organizers of the Boston Scala meetup. Might even still consider himself one of the main organizers. He's one of the organizers for the North Scala Symposium. He used to work for the W3C, and now he works with analytics. About coding, very hard. Isomorphism.
Yeah, isomorphism is basically implicit here.
Anyway, thanks, Alex.
So before starting, I'd like to know how many people here would consider themselves familiar with, Curry Howard isomorphism, at least a little bit. Okay, so that's not a lot of people, but that's fine. I mean, for today, I just want to give you some intuitions about it. We won't go too far. And one thing I want you to remember is, and I will try to explore that, is let's say I have an algorithm and I want to express some properties on it. And I would like to see how it's possible to actually say things about the program without even testing it. Usually, you write an algorithm, have specification, write a bunch of tests, and you get some results out of that. And we try not to do that today. And in order for the talk to remain easy, I would just go with this very simple example, the Euclidean division by 2. I hope that everybody here is actually comfortable with that concept. Should be fine, right? So anybody should be able to implement that. But the meat of the algorithm is just, I try to subtract 2 until I reach 0, 1. And every time I can do the subtraction, I just increment counter. So functional style will do something like that. And yeah, you can see the execution of this program here. Oh, and by the way, if you have any question at any moment, please interrupt me. No issue. So that's not really what we want to do. I would like to have some control, full control over the types that we are using. So instead of just relying on Scala integers, I would define the data type for naturals using the piano encoding. So the piano encoding is just saying you have first case, initial case, which is just 0. And to construct a new NAT, just have the S constructor here. So basically, if you want to encode 2, you would have S of 0, and so on. And I just have, for the examples here, just utilitary function, just an easy way to go from the normal Scala integers to the NAT, so that it's easier to feed my algorithms with it. Actually, this is not really well defined, so we are already getting into troubles with types. This is only defined for I being positive. We'll just assume this is okay. Right. A few operations on the NAT. So you want to be able to do plus, multiplication, and maybe just going back to Scala integers, just for it's easier to print that on the screen. So I'm just writing, defining a wrapper using Scala animal thing, and I'm just so this is just a case. I'm looking at the n and pattern matching on that, and the plus is just fine as every time. So I try to subtract 1 on the left operand on the n, and every time I can do that, I add it on the other side. And at the end, when I reach 0 with the n, I just added everything on the right side, and I have the result of the addition. The multiplication works in a similar way. It's just n times n. It's just like n plus n plus n times. So just using the same thing, I can just encode the multiplication in terms of addition. So a few examples with that. I mean, nothing really fancy. So I'm just injecting the 2 in the naturals, and then just using addition multiplication, it works as expected. Nothing really fancy so far. Now we want to go to the really interesting thing, which is the actual division on the NAT, the way it was defined. It's actually very similar to the first version we had. So first we do pattern matching on the value. We see if we are already 0. If not, well, it can be 1 or something else. So I do pattern matching again. Oh, was it 1? Then I know, for the first 2 cases, I just have, that's the end of the recursion. I can just return 0, because 0. That's the division by 2 for 0 and 1. And otherwise, I call myself recursively, and with basically this n0 at the end, just the -2 of the first, the n I was actually looking at. And so I call myself recursively, and I add 1 to the result. And it was just like before. There is nothing here. No questions so far? I guess shouldn't be too difficult. So we have a few issues here. I mean, if I want to specify that and test that, I would try. I mean, that would be a good first case, right? I start with 0 and I generate a few samples, initial data, and I run the division. I can maybe try to, I can inject that in the integers and see if it behaves exactly just like Scala integers or anything like that. But in my case, I want to actually put that in the code itself, not in test or anything else. So I want to attach basically the property on the result type. So I don't want just NAT. I want NAT plus some properties on it. So I'm just defining this new. So it's just a holder for x and y. So y would be here the result of the computation. X would be the value that you pass to the function. And I put them together so that I can have this property. So basically, this property is a mathematical way to express, what being, y being the division by 2 by x. Actually, this equation, this property should hold. So either the left side or the right side, and y would be the same for the 2. And the algorithm is just the same thing, right? But instead of just returning a y, I need to unwrap the result from the recursive code, and then I need to return another div2 where I put. So my recursive code is here. I get my y, and then I can just return the first one here. But that's basically the same thing as before. But now when I run this program at any time, I would hope that I would have no exception from my Scala. So that's the thing. The idea is there. Basically, tying together the property and the value. The only issue is that I have no way to speak about it outside of the runtime. So actually, you can do that in Scala, or you can do that with a lot of efforts. So just for the rest of the talk, I'm going to switch to the code proof engine. I don't know if you've ever heard about that, but that's actually a very, very interesting thing. So it's based on functional programming a lot, but the type system is a lot more powerful. So you can actually have dependent types. So you have types and properties depending on values, and that's not something you have directly in Scala. And when you do math, you can actually express theorems, and you can actually prove your theorems by interacting with them. And that's what we'll see in the rest of this talk. And don't worry, there will be some Scala at the end. So this is how you would encode the naturals in code. That's exactly, that's it looks exactly the same as it was in Scala, right? Instead of having the attribute data types with seed, trade, and case object case class, we have something more powerful. So here you don't see the full power, but that's enough for our purpose. So we just have two constructors for the values of the naturals, O and S, and we can actually construct those values. And so, for example, here I'm providing a term to change, just a way for code to type check your term that you are passing. So everything is working as expected. If you squeeze a little bit, it's still some Scala, not very far. Fixed point is the equivalent of that's the recursive function. And again, that's exactly the same implementation. I have the left operand, the right operand. I pattern match on the left, and that's how I encode that thing. And so a bit more interesting, instead of checking, you can also compute, right? So here I just have 2 plus 3, and I get 5 at the end, and the type is still nice. So still the same thing, and just getting familiar with the syntax. Nothing special. So that's the big difference. Remember before when we defined div2 to hold the x and y together with a property? Here I will be able to actually have the property part of the type itself. So that's the big thing. That's why I'm using code for this term. So how does it work here? I'm saying, okay, div2 of x. It's like, so I have an x, I have a y. So they are basically tied together. But div2 of x can be constructed with this direct. So there is one constructor for this data type. And I need, in order to construct things, so of course I need to provide the y. I will need to provide the x. I will need to provide the y. Okay, but there is this new thing. In order to construct this div2x at the end, I will also need to provide a proof that this proposition actually holds. So what does it mean? Well, let's try to get an instance of div2 of x. So with a very simple case with 1. Okay, so what does it take? So here we see, it's like a partial application of a function. So I just provided the x, but I still have to provide the y and the proof over there. So, okay, I know that the division by 1 is 0. Let's provide 0. So one step further, but I still have to provide a proof. So what does it mean actually providing a proof for code in that case? So I need to provide a term which type will actually have exactly, will be exactly that thing. That's horrible. So that's what the value, the term actually looks like. And so, and you can be sure that in code actually that's that value here. This whole value, it has exactly that type. So normal humans are not really able to do that. So instead of doing that, actually we can switch to what's called the interaction mode. It's like a ripple, like in Scala, and you interact with with code, and you have this actually a proof in front of you. So that's the proof. Below the line, you have the goal, so the thing that you are trying to prove. Sometimes, you accumulated a few other goals, so you have sub-goals and stuff. And above the line, we have that's actually our context. So things in the context are true, and I can use them in order to prove my goal. So here I'm starting fresh. I mean, it's not really fresh because code is it's like a full language, and it comes with a big standard library. So you have a lot of theorems and functions already defined that we can reuse. It's a toolkit, and we actually need that. So in that case, what do I have to prove here? And my claim is that this thing is equivalent to the function that we defined, the Euclidean division. Just saying, for all x, I'm able to prove that there is a y such that the property actually is true. So that should be more or less equivalent. So what does it mean proving that for x something? Well, it's the same as saying, given an x, I prove that thing. So it's the same as introducing the x in the context and continuing the proof with that. So this is done. So every time you see that, so that's actually the invite for the prompt, and that's the commands I'm giving to code, and code will react to that and say, okay, if it's valid, we are going to the next step. It's like a game. It's very much like a game. And before even going further, so we know that we need some kind of notion of induction or recursion. For in this context, I would say it's more or less the same thing. You know, it's when we have naturals and you want to prove something about that, you say, okay, I have to prove it for the 0 case, and if it's okay, then I have to prove it for I will suppose it works for n, and I will try to prove the same property for n plus 1. And if I have 0 and n implies n plus 1, then it's the same as having proved that for all n. So that would work, but we need something a little bit powerful than that, which is equivalent to that. So if I want to prove that the property is true for any n, another option, instead of just going n 0 and n like n plus 1, it's like to say, oh, actually, given n zeros here, if I was able to prove it for n 0 and all the other values before the n 0, then I have something equivalent. And we'll see why. So right now, it seems a little bit magical. I mean, why would you even need that? It's because I worked on the proof before coming, and I know that I need something like that in my toolkit. And that's already defined in code. So that's the GTWF way. So theorem, which is defined there. That's the link to the documentation. And I can actually rewrite my goal. In terms of that. So it's just about applying the theorem. Applying the theorem is just saying, okay, I have some parentheses, I apply it, and I have new things in my bag. I will go very quickly, but basically applying it and then putting that, the new information in my context. Now I know that I have to prove for n. The same thing as before for n, but now I know that all the n's that are less than n can be divided by 2. And being divided, you can divide by 2 means that I can find a y such the result of the division. So that can be very, very helpful for what's happening next. And the usual thing when you get stuck in a proof, you try, and you know that you're working on some type or whatever, you start throwing the induction command saying, I want to reason by case. So that's the n plus 1 and the 0 case. So the first case here will be the 0. So see, I have now 2 goals. I have the 0 case and the s plus 1 case. So now I have to prove that this thing is true. Usually when you have single values like that, where it's very easy, you just have to exhibit the something that would comply with that. But that's pretty easy, right? We know that 0 is divided by 2 is 0. So I just have to use my constructor with 0. Div_x was the constructor for div2, the only constructor we had. So I'm just saying, please use 0. I know it works, but that's not enough. Remember that in order to have the full div2, I had the second part, which was the property. So I still had to prove that the property is okay for 0. So do you think it's true? Well, that should be pretty easy, right? The left part is obviously true. There is a little bit of work to do that. So first I have to say, okay, I think I can prove the left part, so I'm going with left. When I've done that, the 2 times 0, I can rewrite that as 0. Then I have 0 equals 0. That should be pretty obvious. That's by reflexivity. I have proved actually what I was doing. So I'm just saying, okay, I'm done with that. And from 2 goals, now I have only 1 goal, so I'm switching to the second one. So that's the recursive case. But actually, so this is not enough for us. What we do is actually we go with a single induction. You know, that's the case. We had the case 0, now we go with the case 1. But that's pretty much the same thing, right? So now we need to provide a proof for 1. Well, we know it's actually 0 again. We have the same thing. You know, we need to prove this time the right part of the property, and it's a one-liner in that case, and I'm done with that. So now I have the need of the proof, which is actually the case n plus 2. And remember, we still had this thing in our bag. So that's very interesting because we know that for any n that is actually less than this guy, I can find a y. I mean, I can divide n, and I can find a y for that. So that's pretty cool because if I can find a y for this one, well, I know that I have, for example, I don't know, 4, okay, and I know that when I divide by 2, it's actually 2. Now, if I say plus 2, I have 6. It's just 2 plus 1 would be actually the division. So I just have to add my 1 here. So that's pretty easy. I'm just saying I need to find this y in my context. So I'm finally using the hypothesis we had. And now I have this y. It's in my hand. Actually, I don't know exactly what is the case. I have to make a choice in order to prove that. So it looks pretty easy, but when I unfold actually when I say okay, it's y plus 1, and then I have to prove that. Well, it looks easy, but I have to make a choice and see. I have 2 branches in my reasoning, my proof. So I have to try with the left part, which will help me to prove the left part here, and I will have to try with this part, which will help me prove the other part. So in order to do that, I just have to destroy the OR, and I have 2. I mean, it added a code for me, and so this one is pretty easy, right? I mean, if you just think a little bit about it, it's super easy, and that's an easy way to get the proof for that thing. Just going a little bit faster. The right part, so now that's the proof for the right part. I'm going fast on that because it's seriously, it's boring. This part is boring. Code is able to do that even by itself, even from the beginning. But now the only thing I have to prove is that because when I applied my hypothesis, I was still hoping that this was true. If it's not true, well, I'm stuck. But obviously this is true as well, and code is able to do that automatically. So now I'm done. The proof is done, so I can ask for, I can close the proof by using QL, and you have a full script for the proof. So now let's focus on what happened there. A few steps was just playing with the environment, so not really interesting. But the other thing, actually very important for the proof. So what you have actually highlighted here, first we have the use of recursion or induction principle somewhere. Then we have reasoning by case. So the first time here, the second time here. So we have the case 0. Then we have the case 1 and the case n plus 2. In order to actually finish that branch here of the proof, we had to provide an actual value for the proof. So that was the 0 and again the 0. And then that was the case, providing from the code, the recursive code. I had found the y, and I can use that y to provide the last part of the proof. So that really looks like a program, and that looks exactly like the program we had at the beginning. Well, there is a good reason for that. So that's actually, what the Curry-Howard isomorphism is all about. Is that this proof that we are actually constructing is actually just a program. The type for this program is actually the theorem that we had at the beginning. All those things, they are very, very tightly related. And you can go back and forth between those if you're in the right framework. So what it means is that sometimes you can go from code to another, another language that is not as powerful, but you can actually focus on the computation. So from the isomorphism, you can say, oh, please extract from the proof of the Euclidean division something in Scala, and you get something like that. So remember that the NAT constructed now is actually normal algebraic data type. Interestingly here, the div2 that we define with the with property, somehow Koch understood that the y, the x and the property were not helpful at all for the computation. That was something that was useful at the type level. So type means theorem. So that was only useful for the theorem. But when you do the computation, well, you can just throw that away. So it's doing that for us. And then at the end, you recognize exactly the same algorithm. So you can ask yourself, did we do something? That's where we spend time actually adding these properties, and now it's good. Well, it's because the properties, in any case, they don't live in the computation. The only thing is, if you're actually if you stay in Koch and you are using what we define, you would have access to the invariants in other programs, so that would be very, very useful. In this case, the only thing you can say is, don't need to write any tests. Don't need to write any tests. And that's more powerful than any testing framework, because we proved that it can work for any NAT.
Yep. You still want to write tests because maybe you proved the wrong thing.
Okay, so that's a good remark. No, actually,
it's a real problem. Sometimes you prove something.
Well, in that case, you would test exactly the same properties, right? Yeah. So the question was, you might want to write tests because you might be actually proving the wrong thing. Well, the thing.
In terms of the testing specification rather than which is hopefully used.
So there is always this tension, right? But a proof and a test are actually right up to what you specify. If you specify the wrong thing, and that's the same thing for the proof, for the theorem and the test, you're just testing the wrong thing. That's exactly the same problem. It's just usually easier to just run a program and check, if it does the right thing.
So, yeah, exactly. So a quick check is sort of you have a counter, can you give the counters? So even if you prove something, still using counterexample generation is really hard.
Yeah, so there are limits to both approaches, clearly. There is a field of research trying to just exhibit counterexamples. So they do testing just to prove that. But that's not really I'm just saying that in this specific case, the specification was the theorem. So I don't need to write an equivalent test for this property. If that's better phrased, I think that's true. Yeah. So the only thing before I'm done with this talk, I lied a little bit. So there is no, at this time, Scala extraction from Koch. There is, maintained in Koch itself. You have OKML and you have Haskell. Some people provided Clojure, that kind of things. Or scheme maybe.
Extraction. There's actually coding work for Agda potentially to use GHC as a code gen back. Still in the speculative state. But
so Agda would be able to do that? I don't know. Actually, there is. Okay. And some Japanese guy actually tried to implement that, but it doesn't extract. It breaks the extraction even for OKML. So the term in OKML or Scala are just broken. So I couldn't use that. I don't think it's difficult to do, but still. So that's all for today. You can find the slides at this URL. And I'm welcoming questions. questions? Okay. So easy.
So you were talking about abstraction, or extracting that into different languages. So the idea is that you write a proof in it using Puck, and then you can run some kind of interpreter on it that will generate a program in a different language.
Yeah, so the question is about extraction. So yeah, if you want to use it.
Extraction isn't very pretty usually.
Yeah, very few people actually do extraction on a regular basis. There are good reasons to do that. So usually they wouldn't do that this way. Now in Coq, you could program something that looks a lot more like OKML or Haskell or something like that, plus dependent types and other things. So you would have basically the algorithm already in a form that you can understand. And you would have the proof actually still be around there because you can express that in the types. Now there is now a mode actually where you can just implement the algorithm, and it would generate the few theorems or sub-goals and stuff that you have to prove in order to have the complete algorithm being defined. So it's more the appropriate way to do that instead of just relying on Curry Howard. I mean, going with the theorem is not always the best approach.
So to elaborate on that further, at least if I understand what you partly addressed, with Coq or Adder or whichever of these higher order logic do, the proof is actually programmed literally. But when you do the extraction, depending on the target language, you wind up having a lot of things that aren't typable in the weaker reasoning machinery of that language's target type system. So even ignoring whether the algorithm is efficient or not, it's also going to have a lot of magic, coercive kind of things. If you look at the extraction of, say, Haskell or OCaml, because the external languages that those expose the end user are strictly less expressive than things you can actually construct in Coq.
Yeah. So the question is about the target language and the expressivity of the type system. Yeah. In many cases, you would actually lose some information, so you would have to rely on tricks.
Well, no tricks. Just say trust me.
Yeah, it's trust me. Yeah. I mean, you have to rely on the extraction being okay and knowing the semantics of the target language. And you say, okay, the user shouldn't look at the text. Coq actually did everything on that side for me.
Subject to the translation being correct, it then becomes code that you never want to touch. You just want someone to generate that, wrap it up and hook it into whatever else you do. So if you have a proven correct implementation of taxes, you never want to tweak it unless you also prove it correct or something.
Yeah, and then you get into other questions. Does the extraction for your language is actually correct itself? Because otherwise it's basically useless. You have plenty of interesting questions. Any other questions? Right. Okay.
Thanks.
Thank you.